Hi everyone, Krishna this side. In this video, I want to cover this Fenwick tree concept, which is also known as binary index tree. And yes, we will solve a lead code problem as well based out of this one. This problem 307 we already solved with the help of segment tree, but in this video we will solve it with the help of Fenwick tree concept. Okay. And once you guys get the idea about this Fenwick tree, I am sure that whatever the today's lead code problem that we have, which is actually a bit hard to solve and it is tricky, we will get some intuition about this. Okay, we can try it out with this Fenwick tree. Okay, so once I solve this, I explain this concept, Fenwick tree concept, we will try that particular problem as well today. Okay, so yes, let's understand this Fenwick tree concept. So yeah, where it basically get used is like whenever if we have some range, given range in which we have to perform this sum, we are asked to get this sum and all. Okay, so yes, there we can use this Fenwick tree concept. And whenever we need to require update frequently the array, get the sum between the range, whatever the range they are given, we can use this concept. Okay, so already in the segment tree I explained two different logics. The basic idea that we can get is like we can get the range from this array, whatever the range that we have, we can keep on adding them and get the sum. But what if there are thousands, hundreds of the same operations that we have to perform? There definitely it is going to be costlier, right? Because it is going to take I mean it is going to take big of n operations to do the same operation, right? So and to keep on doing this, we have to go through the array again and again and get this sum. So that's going to be quite costlier compared to this segment or this Fenwick tree concept, right? Update is going to be obviously taking big of n, but another approach that we can follow is like we can keep on adding these values, like at 0th index it is 7, at here it is going to be 7 plus 2, here it is going to be whatever the value previously we got, 9 plus this one. So that way we can create another array where we can have the sum. At last index it is going to be sum for all these values, so that way this array value got updated. Okay, now whenever they ask to get the sum from L to R, we can go at that index, and from this index we can simply get the sum. For this last index it is having the sum till this index, and for this third index it is having sum from this to this. So we simply can get sum till this, and all these are overlapped values, right, from second to till 0th index. So we can simply subtract the value whatever that is available at the second index. Okay, that way also we can get it, but their problem is with the update. Okay, so the moment they ask to update any value from the array, we have to update the whatever the array that we have created, all those values as well. So there it is going to take big O of n, right? So if there are r times operations that we have to perform, then it is going to be n cross r. That is the complexity that we will be having. So that is also not appropriate. So yes, we will be going to rely on this Fenwick tree. Okay, segmentary concept I already covered it, and it is basically going to take 4 cross n space approximately, which is quite costlier compared with this Fenwick tree, because in Fenwick tree we will be using space big of n. And yes, we will try to solve this particular problem. Okay, whenever they ask to get this sum from given range, we can easily get them. Okay, so yes, using Fenwick tree, update and query will take log of n time. Okay, we will understand how it is going to take, and it is space efficient, as I already said, because it is taking big O of n. Okay, n plus 1 is the space that we will be having, but it is, yes, of course, n. So now how to store whatever this arrays information in Fenwick tree, right? That is the first thing. Okay, so we can create a tree of n plus 1 size array. At 0th index, whatever the 0th index array value that we have, we will start storing it from the first index from this tree. Okay, that is the first single thing that we have to remember right over here. We use this LSB, so least significant bit technique, to store the values. So yes, this is another concept that is available in bit manipulation. So yes, few concept that we need to already have idea about this bit manipulation before solving this particular problem. And I'll explain you there are certain operations that we have to perform to update these values into this tree of whatever the array that we have created, and that we will have the idea right over here. Okay, so we will start from this 0th index, that will be first index. So the I value is basically 1 for this tree. Initially we fill it all these values with 0 in this tree value. By default it is basically 0. Now what we do is I is basically 1, and the size of array is basically 8. Okay, the value is basically 7. So 7 is something what we will update in this tree. Okay, so how we do that? Okay, so the first thing is I should be less than or equals to n. Whatever the I value that we have, it is basically 1, and since the tree value is basically n plus 1, so we can go till n plus 1. Okay, I value, and the I value, the way we will jump is like I plus I and I minus of I. Okay, what it is basically doing. Okay, so yes, we'll try to understand this, and by end of this video I guess you guys will get the concept what it is basically, and how we are dealing it with. Okay, so this I and minus I gives us least significant bit that is available in this particular I. What it is means, okay, let us suppose I is basically 7. Seven's binary formation is basically 111. That is the least thing that everyone should have idea about it. Okay, how to convert whatever the value that we have into this binary formation, because the data basically stores in binary formation in the memory. So yes, everyone should have the idea like how we can convert it into the binary format and all. So 7 is basically 111, and negative of 7 is basically we can say that it is basically 2's complement. So any value that what whenever we say, right, like a value that we are storing it in memory, negative value, right? So what we do is basically we convert that value in 2's complement, and that is something what whatever the binary formation that we get, that is something what gets stored into the memory. So let us see, 7's value is basically 111. So it's one's complement is basically what we can do is in the one's complement, all the one wherever we find that one, it get converted into the 0, and 0, whatever the value of 0 is there, it gets converted into the 1. So we just switch the bits, we flip the bits. Okay, so now here all three are 111, so they got converted into the 000. So this is the ones complement. Okay, the moment we get to ones complement, we add 1 into it to get the twos complement. So now this is the twos complement, and which is the negative value that is basically represented in the memory. Okay, so negative of any value is basically 2's complement. That is something what we have to consider over here. Now we got the 2's complement, and if you remember here, the least significant bit is basically here from here, right? 111, which is the least significant bit. It is 1, right? So just consider that here instead of 1, the least significant, the cursor where it is pointing. Okay, here from right over here, this instead of 1, if it was 0, so from this 110, the least significant bit is going to be the middle one. Okay, if this is also 0, this is also 0, the least significant bit is going to be this one, the 110. From 110, the first from the left side, the first one that we got is going to be the least significant bit. Okay, the rightmost bit that is active, that means it is having 1 as a value, that is going to be the least significant bit. Okay, so that is something what we get it from 7 and minus 7. Okay, if we do this AND operation, now we got this one, right? That is something what we are trying to figure out. Now the moment we got this value, that is something what we are adding it into the I. Okay, so we are keep on doing this operation until we go out of index. So whatever the I value that we are going to get, so this I value we keep on updating it. Okay, so now I is basically 1. So let us look into this one. Okay, I value is 1, so tree of 1, at first index we update the value with 7. Okay, the tree's value of basically it was 0, so it got updated to 7. Now I basically we are performing that operation. I goes to 1 plus 1 and minus 1 is going to be 2. Now again we go and jump on this second index and we update it. Okay, the moment we get the value, we go we check that if it is less than or equals to n. Yes, it is less than or equals to n, so we update the tree's value with the 7. Whatever the previous value that it was holding, we are adding it with 7. The moment we do that, again we do the same operation. 2 plus 2 and minus 2 is basically 8. Sorry, it is basically 4. So again we go and fourth index, we update this value with the 7. Again we try to update it. I is basically 8. We go update the 8 value with the 7. Now we again try to do the same operation, but now the I value is basically 16, which is actually out of bond, because n is basically 8 and the i's limit is still 8. And of course once we get out of bond, are we really necessary to store these values? No, right? So yes, that is something what we are doing right over here. The moment we do that, these values get updated into this array. Now this for the first index value, that whatever we have, we updated it according to this. Okay, the moment we update these values according to this, okay, the first index got updated to 7, second index got updated, fourth index got, seventh index, we will start looking for the next index. Okay, the next is, it is basically 2. So I is basically 2 now. Okay, now the moment we get I as 2, what we do is basically, hold on, wait, I'm getting the call. Okay, I'm back. Yes, where were we? So we will be now start looking for I equals to 2. Okay, so the value I is actually 2 now for the second index. This is the value that we want to update into this tree. So yes, again same thing we will do. I equals to 2, n is basically 8, the value is basically 2. 2 is something what we have to update into this array. So the tree is now tree of I plus equals to the value whatever we have. Tree of 2 is basically updated with the 2. So it was previously 7. So 7 plus 2 is basically 9 is something what we updated. Now I is basically pointing to 4. Same thing that is happening right over here. So tree of 4 plus 2 is basically 8. Now the I is basically 8. Okay. So tree of 4 got updated with 9. Now I is basically pointing to 8. Now tree of 8 plus 2 is basically 16. So 16 is out of 1. So we are coming out of this loop. Okay, now for the third index, whatever the value that we have, that is 4, is basically what we will be updating into this Fenwick tree. So the value is 4. Tree of 3 is now basically got updated with 4. Okay, so we are getting some idea, right? So first index is basically holding the range from 0 to 1. Second index is holding range from 0 to 2, because 1 is value is something what it got updated already, right? Now the third index was 0 so far, but now it got updated with 4. Okay, so it is holding the range from 3 to 3. Basically the only value that it is holding is third index value only. Okay, but second index was holding value from 0 to 2. Okay, this is basic thing that we need to consider right over here, that will be help us in the future. Okay, now the value of I is basically 3 plus 3 and minus 3 is going to be 3 plus 1 is basically 4. So you can consider here as well. 3 is basically represented in this way, 0 1 1 1, and minus 3 is basically 0 0 1. So least significant bit is 1 only, right? So that is what we are doing. So 1 is what we get, and that is something what we add it with this I, previously value I. So it is basically 4 now. Now tree of 4 is something what we update it with its value. So previously it was 9 plus 3 is basically 13. Now here we get that this 4 is basically holding values from 0 till fourth index. Okay, the moment we get I equals to 4, we are getting going to update this value of 4. Okay, so it is holding the range from 0 till fourth of this index. Okay, this is a particular thing that we need to consider right now, that will help us in the future. Okay, when we try to get the range query, we will understand that okay, it is how that is how basically this is how it is holding these values. Okay, so all these operations, when we start with this first index, right, it was basically taking log of n time. Okay, so we update 1 2 4 8 16 if possible, then 32. So basically we are jumping across 2's power. Okay, so it is going to take log of n time. When we start with the second index also, this is basically also taking log of n time. 3 is also taking log of n time. Okay, now when the moment I is basically 8, we update again I's value with whatever the previous value it was. So 13 is what we have. Now when I is 4, n is basically 8, value is basically 3 at fourth index, that is the third index from the array. So we update the trees value with the tree. So previously it was 13, now it got updated to 16. So from the 0 till 4, all the values, sum of these values is basically it is holding. Okay, 3 is basically holding till 3 to 3, 2 is basically holding from 0 to 2, 1 is basically holding from 0 to 1. Okay, that is pretty much the idea that we got by doing all these operations. Okay, now we will do same until this all the arrays value get filled into this tree of n plus 1. Okay, that is the update operation that we are doing. Okay, let us write down the code as well. In the coming time, I'll explain you in detail. Okay, whatever the operations, the code that we are doing, but side by side, let us write the code as well. So I'll create a Fenwick tree class. In this class, what we do is we will be having this tree. Okay, or else what I do is, instead of creating this class and all, okay, we can do it in fashion way. Okay, and that is the best approach to write the code. Okay, but right now what I do is I'll create here only a tree. Basically it is holding the value So what I do is here inside here the trees I'll initialize this tree with nums dot length. So what I do is I'll get n. So n will be getting updated with nums dot length. Okay. Now we have nums dot length. What we can do is basically we update this tree's length with 1, and again I just want to hold a copy of this array as well. Yes, we can deal it with, but yes, now I just want to hold it because in the update I don't have really hold about this nums of I, so I just want to update its value there itself as well. Okay, doesn't matter if you want to hold it or not. There are ways where we cannot even don't want to hold it. So what I do is this copy is something what updated with the nums. Okay, now this is something what I have done. So I want to create a build function which basically keeps on updating into these values of the tree. So we can name it as build or update anything. So I'll do is I'll pass uh, what we do is from the 0th index we are going, right? So int I equals to 0, I less than n, I plus plus. So what we do is basically we call this build function. We pass I, then we pass this nums of I, whatever the value that we have. This is something what we want to update into the tree, right? So what we do is here I'll create a public void build function, and we have this I, then we have int val, that is something what we want to update. So by default I is basically 0, so I want to start with the first index, so I updated I value right over here. So either of the way we can do it. We can pass there, yeah, we can manipulate this size value, right? Which the index is now pointing to 1. So in the tree what I do is tree of I plus equals this val. This is the first option that I want to do. Now I want to do is I want to update this i's value, right? So I is basically how we are doing I equals to I plus I and minus of I. That is what we are doing. And I want to keep on updating this value. So what we do is we will run a while loop. Inside this while loop, this I should be less than or equals to n. That was the condition that we were having, right? So till it is less than or equals to n, we were updating these values into the tree. We were keep on updating the value into the tree, right? So that is as simple as this while loop. Okay. So whatever we are doing, so I should be less than or equals to n, and in the tree of I, we were keep on updating whatever the value that we were having, and I value is something what we are updating. Okay. So this is how we build the tree completely. Okay, 0th index value we build it with. So this is taking log n time. So again, first, second, third, all these values basically takes log n. So this for loop and this one takes n log n. We can basically convert this into the log. Sorry, it we can convert this into purely into this big of n also. But that is another way to do it. So currently, I am building this tree based on n log n. Okay. But yes, we can run two for loops. In the first for loop, we can simply copy all the values into the tree, and in the second for loop, whatever this operation that we are doing, we will simply update that particular index value with the current value that we have. Okay, what I'm trying to say is I can write down the code as well. So okay, I'll write it down in next coming videos. Okay, what whenever we get this Fenwick tree, but the idea is pretty much simple. I whatever I explained you, create a first for loop. Inside the first for loop, just copy all these nums of i's values into the tree, and let's go through the for loop again. In the another for loop, what we can do is for at first index we are at, so whatever the value that we have, just get this i's value in the particular tree's ith index. We can update this value with this current value that we have. Okay, we will sum it up with that value. So if at first index value is 7, at second index value is 3, and when we loop again the second for loop, when we loop it, so at the first index whatever the 7 value we got, I value will update it. So whatever the I value that we got, it is going to be, let us suppose 2, because 1 plus 1 and 1 minus 1 is going to be 2, right? So basically at the second location, what we do is 7 value, we will increment it with whatever the value currently we have. It was basically 3. Okay, it sounds a bit complicated because I couldn't explain it properly, but yes, that is the idea that we can follow. So this particularly a for loop, and this one takes n log n, but whatever the approach that I had told, that is going to take b of n. Okay, I'll write it down at the end of the video. Okay, anyway, we don't have to worry about it. But basically, we build the entire tree. We have the tree now. Now the next operation is update. So basically the update is basically following the same build approach, right? So we, whenever we want to update any value, we will be updating the values and current value, and we keep on jumping into this next values where basically this i's value is relying. Okay, what I'm trying to say is, see, if they ask to update first index value, so basically which all index basically gets modified when we are trying to update the first value. The first index definitely get updated, the second index should be updated, fourth index should updated, eighth index also should updated. So basically the update and this build is basically the same functions. Whenever they ask to update, we can just use this one. So this particular technique takes a log of n time. So whenever we have to update the function, we will basically run this, build this, and pass the index, whatever the index they are asking, the value is something what we will pass, so it will do our operation. Okay, so when they ask to update the first index, definitely for the first index, which are all index are dependent, second index is dependent, so in the second index we will simply update, fourth index we will update, eighth index we will update. But here the catch is, so whatever the previous value that we have, okay, so previously there was some value, and we are now updating these values. Okay, so in the uh, this trees function, the all values are got modified slightly different. So what we have to do is, whatever the previous value that we have, we will simply subtract with this current value from the copy function. What I do is, this copy array is something what we have, right? From this copy array we get that new value, something what we want to update it into the current array, right? So let us suppose currently it was 7 at first index, and they are asking to update it with 9. So what we can do is basically get the new value. So new value is basically this val minus copy of that previous value. So previous value at that index was basically, let us suppose it was 7. Now new value is basically 9. So 9 minus 7 is basically 2. So 2 is something what we want to add on, because this is basically keep on updating it, right? So let us suppose the current value is, let me write down here. Uh, let's say previously at first index the value was 7. Now the new value they are asking is, at first index they are asking to update with this 9. Previously it was 7, and based on the 7 we keep on adding the values in those arrays. Now they are asking to update it to 9. So is it easy to directly add 9 into the previous value? No, right? So previously it was holding 7, and that is something what we are keep on adding it. So now what we do is basically we subtract 9 to 9 minus 7, that whatever the new value that we get, that is something what we will add it into the tree. So 7 was the previous value, new value was 9. So what we got, minus 2 is something what we got. Minus 2 is something what we will add it into this tree of array. Or sorry, it was vice versa, right? So whatever the new value that we got, 9, and previously it was 7. So 2 is something what we got, right? So 2 is something what we have to add it into the tree of val. Let us suppose now the tree value was 7, so it got updated to 9, because this is the new value, that is something what we are passing. So instead of val, new value is something what I pass here. Let us suppose if the new value is something what 4. Okay, previously it was 7, and this is another example that we saw. Now new value was 4, so 4 minus 7 is what we get, minus 3. Minus 3 is something what we will keep on adding it into the tree of each respected index. So previously it was 7. 7 minus 3 is basically 4. So at first index the value is going to be 4. Now in the coming indexes as well, we keep on subtracting minus 3, because we are actually reducing from the 7 to 3, right? And we are adding it. It is not directly we are assigning the value. So yes, of course, whatever the previous value that we have, we need to subtract from the new value, and whatever the new value that we got, that is something what we have to keep on adding it into the tree. So that's why we actually need to get the new value. Okay, and that's why I actually created a copy of the array as well, so that I can get the copy of that particular index. And what I can do is, now copy of index, I'll update this as well with this var. Okay, in the copy index we can update that whatever the new value that we have, but whatever the new value that we are getting from the copy index, we need to subtract it. Okay, that way we can update it. Now the build function is done, so we need to get the sum query. And yes, we have to remember that each index basically holding some ranges. So first index is basically holding the range from 0 to 1, because it is having only 7, that is the 0th index value. At second index, it was holding value from 1 to 2, yeah, 0 to 2. Okay, we can say that 0 till 2, all the values that the sum that we have, that is the sum that is holding, it is holding, right? Because i's value we updated at the second location. Now second location's value also we updated into there. So it is holding the sum from range from 0 to 2. Third is basically holding the sum from range 3 to 3, because it is having only third index value only. Okay, this ranges is something what it is basically all these indexes holding. The fourth index is holding the range sum from 0 till 4. Okay, that is why it is having 16 value. Okay, so yes, this is the range that it is basically holding these trees values. So now we need to look into the sum functionality. Okay, so what we can do is let us look into this particular image. Okay, so if we start focusing into this image, the final tree that we got is basically at 0th index it is 0. Definitely we are not worrying about it. At the first index it is 7, second index it is 9, and so on. So we keep on doing that operation, and this is the final array that we got from this previous array that we are looking at. Okay, the final array, once we get it, so as I already said, the first index is holding range from 0 to 1, second index holding range from 0 to 2, third index holding range from 3 to 3. That means like the range is like the sum values basically. Okay, here it is 4, that means 3. Third index value is basically it got updated, right? So its range is like from 3 to 3 only. Fourth index is holding some from 0 till 4, so its range is from 0 to 4. Fifth is holding some from 5 to 5. Okay, because it was already 0. Now the whatever the new value that we got, we simply updated it into the fifth index. Okay, so its range is 5 to 5. Sixth index range is actually 5 to 6. Okay, so that's how the range is something what we have in this array. Okay, that is the idea that we have to remember. Now they ask, if they ask to get the sum from range 3 to 5. Okay, so if they ask to get the sum from 3 to 5, so fifth index, what we can do is we will get the sum till fifth index. So whatever the sum that we get from 0 till 5, we will get the sum first. And what we do is we will get the sum till 3 to 3 minus 1. So basically, see, since it is both inclusive, so if we want to get sum from 3 to 5, 3 is something what we have to consider. So I cannot simply subtract sum till 3, right? So I have to get sum till 2, because 0, 1, 2 are the overlapping for this 3 to 5. Because when we get sum till 5, it is not, so don't rely on this array. I am just saying that we need to get sum till 5. Till the fifth index, whatever the sum that we get. Okay, currently at fifth index it is 7, but we have to make sure that we will get sum from all the array till fifth index. Okay, that is something what we will see, like how we will get this sum. But yes, we have to get sum till fifth index, and we will subtract it from sum till 3 minus 1, because 3 is inclusive, so we have to consider it. So 3, 4, 5 are the elements that element sum is what we have to get. So what are the overlapping elements? Those are 0, 1 and 2, right? So yes, get the sum till second index, and 1 and 2 are overlapping because they are overlapping. So whatever the sum that we get, when we subtract it, that is the sum that we have to return. Okay, so yes, this we got. Now how to get sum till fifth index, right? And how to get sum till second index. So there is a particular formation, like how we will see here. Sum till fifth index, if you want to get, so go to the fifth index, get the value. Currently we will denote a sum which is having 0 as value. Now what we do is whatever the value at fifth index, we will get that and add it into the sum value. So it is 7 basically. So 7 is what we added into the sum. The moment we add the 7 into the sum, what we do is again reduce this I value, whatever the currently I is basically 5. So reduce the I minus I, and I minus I. So basically when we are updating, we are adding here. When we are when we are querying, we are subtracting, because we need to go backside now. There we went forwarded, now here we have to go backward. Okay, when we were updating in forward fashion. Now we have to get values from the backward direction, because fifth is basically holding range from 5 to 5, and it is not holding for, we need to get the sum from 0 to 4, right? That is something what missing here. So we get whatever the value that is available at 7th index, fifth index, and that is something what we added it into the sum. Now we again, if we do this operation, I minus I and I minus of I, what it does, 5 minus 5 and minus of 5, basically 1 0 1 0 1 1, it is basically 0 0 1. Okay, So this is like the least significant bit. Again, we are getting it, and it is something what we are subtracting from here. So what it gives us is like 5 minus 4 is 4. 5 minus 1 is basically 4. Okay, sorry for that. 5 minus 1 is basically 4. So 4 is something what we again go and at fourth index, whatever the value that is there, that is something what we add it into the sum. Now we go into the fourth index, get the value of sum, reduce I to I minus I and minus of I. So again, my 4 minus 4 is basically it is basically gives us 0. Okay, because here sorry, it is going to be give us 4. Okay, sorry for this wrong interpretation. So 4 is basically 110. So when we convert it into ones complement, it is going to be 1 is getting converted into the zeros, and all zeros get converted into the 1. The moment we add 1, it is going to be 1 minus 1, and 1 it's going to be 0. Then here it is going to be 1 again added at the top. So 1 plus 1 is 0. Again 1 added here. So 1 is basically 1. So minus of 4 is basically represented as 111 100 only. So 2's complement of 4 is basically 2 only. So now this particular form is basically giving us 0. Sorry, this particular is basically giving us 4 only. Okay, 4 and minus of 4 is basically 4 only, and that is something what we are subtracting. 4 minus of this 4, that is something what we get. 4 and minus of 4 is basically 4 only. So when we subtract, we reach to the 0th index. The moment we reach to the 0th index, we got the sum. Because see, 5 is something what covering 5 to 5 range. Now we shifted at 4th index. 4 is basically covering the sum from 0 to 4. So the moment we reach at 4th index, we add it into the sum. So previously sum was 7. Now when we add some whatever the value that is there, 16, into the sum, now the moment we do this particular, right, so what it does is it takes us to the 0th location, because it is basically holding range from 0 till 4. Okay, that is the catch here. Okay, the moment we get this, the sum till 15 is something what we figured out. Okay, so yes, again here while updating, we are just adding here plus 1, while getting the range from that particular index till back of the 0th index. Here we are just simply subtracting and keep on getting the values and adding it into the sum. Okay, till 5 we got the sum. Now till 2 we again will get the same thing. So at the second index, whatever the value that we have, it is 9. 9 is, once we get the 9, when we do this operation, right, for the 2, it is going to jump to 0th index basically. Okay, so 0 to 2 is what the range that we have. So we basically jump to the 0th location. The moment we reach the 0th location, whatever the value that we get, that is 9 is what we got. So this is still this sum till the second index is some basically 9 only, right? So that is the what value that we get from here. So till 5 we got already whatever the value that we wanted. It was 23, and here it is 9 basically. So when we do that, it is 14. 14 is something what the sum that we have to return. Okay, that is how we can write this code. So let us write the code first, and again we will discuss about the logic. So what I do is I'll create public void get sum. Okay, I'll be having index that I denote as I, and yes, we have this tree already. So here inside this I, right, so basically it starts with the 0. So we have to, I mean, the index of whatever the values they have given, they are basically starting from the 0. So we are incrementing it. The moment we increment it, we run a while loop. In the while loop, what we do is basically I should be less than or equals to n. Okay, n value is something what we already defined outside. So yes, we don't have to worry about it. And inside here, what we do is let us create a some function int sum equals to 0. So it is basically integer type. So the moment we get that, we return it from this sum. What we do is basically we add into the sum whatever the value that is there in the tree of I. The moment we get that value, what we do is basically we uh, change this i's value. So I and I minus of so I and minus of I. Okay, that is something what we have done it, right? So we go to the previous location till the range that is holding few of the values. Again, once we get that, we again jump to the previous location. So this is again like log n time it will take. So yes, the sum is something what we get from here. So what we do is we return uh, so get sum of left, sorry, it is right, right, and then get sum of left minus 1 is something what we are doing here, right? So that's it. So let us run this code first. Let's see if there are any issues. So okay, there are errors. Okay, line number 9 tree equals. Okay, this is not how it should be written. New int n+1 copying, we are doing build, then update, and we are getting the sum. TLE is something what we hit with. Okay, something went wrong. The while loop is basically going wrong somewhere. So it is not like this, right? So sorry for this mistake. I should be greater than 0 during the get sum because we are going backward and we are decrementing the I value, right? Here we are incrementing and it should be less than or equals to n, but here we are decrementing, so I should be greater than or equals to greater than 0. Basically, at the moment we reach at 0th index, we are simply going out of this loop. Okay, yes, it got accepted. Let us submit this code. So it is basically taking log n time, as I already said. This particular operation that we are doing, okay, this particular build operation is basically taking n log n. Okay, but we can improve it. How can we improve it, right? So what we can do is, let us in this first for loop, what we do is, in this tree of I plus 1, there itself what we do is nums of i's value, and what we will put. The moment we put these values, we will be having a tree with us. Now what we do is, another for loop we run for int I equals to 1, I less than or equals to n I plus plus. Now here what we do is, tree of I is something what we will get the next I index for this current one. I equals to I plus I and minus of I, and whatever this value we get, we store it in another variable j. And what we do is, tree of j is something what we update with this current value, whatever we have currently. Tree of I, whatever the value that we have, that is something what we update. So now second index got updated with this previous value. So whenever we are updating with the fourth index, whatever the value that is there at second index, that is something what get updated there. Okay, this way also we can do it. Okay, we don't have to update it in this fashion. Okay, yes, this is the build function. Now it is taking big of one time, big of n time. Previously it was taking this n log n, because I was directly relying on this update function, or whatever we are doing it. That way also we do it, or this way also we can perform it. Okay, there was an error here again. It is out of bound for index 4. Okay, why it is saying so j equals to, yes, we have to check that if j is less than or equals to n, then only we have to do this operation. Okay, so yes, that way we will keep on updating these values. Let me run this code again. It should pass. Yes, let us submit this code again. Yes, as I already said, it is taking this update functionality is taking basically login time, and even the get some functionality is taking login time. Okay, so yeah, that's all from this particular video. I hope you guys get the idea about the Fenwick tree. There are pros and cons as well regarding this Fenwick tree, because it is not going to be used in min max range queries, which was where the segment tree basically works. But those things we will cover in future videos. But for now, I hope you guys get the idea about the Fenwick tree. It is pretty much easy and straightforward concept, but yes, few of the things needs to be considered before solving this one. So yeah, that's all from this particular video. I hope you guys get learning. Thank you for watching this video. Bye bye.